start. And thank you very much for coming. I'm very happy to see a lot of new faces here, and we're very happy to start our quantum club again this semester. And the first talk is given by Roope from now, I guess, officially in the group of EPR, but he's moving soon to Stockholm for professorship position. And we are very happy to have a chance to have Roope here today. And the talk is going to be about quantum theory, quantum locality, entanglement, and balance inequalities. So, Roope, all is yours. And
yes, thank you very much for the introduction, and thanks for so many to come and see this talk. Wonderful, see many faces. So I was asked to talk about EPR paradox. The EPR stands for the names of the paper from 1935, so quite long ago, Einstein-Podolsky-Rosen. So I thought that I will talk about it from my perspective. So I did research on this topic from the perspective of quantum information and also from this perspective of measurement incompatibility. First of all, what is the EPR paradox? I will get into it in a bit more detail, but the idea is very simple. In this paper from 35 by EPR, they sort of got to a conclusion that the quantum mechanical wave function is not a complete description of physical reality. There should be another theory that is more complete. And if you think where you might have seen this before, you haven't heard about it, it's a typical example of having maybe in your lecture or then just in a science documentary that you have two particles, maybe two electrons or two photons which are far away from each other, and you measure, say, polarization of a photon of one particle in direction Z. You know instantaneously that if I were to measure on the other particle the same measurement, outcome would be the same. Same if I measure the spin in any direction, or polarization in any direction. And so this is an effect which includes two parties. So it's maybe a little bit surprising to see here that there is measurement incompatibility, which is a single party property. But as you will see throughout the talk, actually mathematically they are absolutely equivalent problems, so there's no difference. So as I understood that in this talk, many times there's sort of a warm-up talk, which I didn't come up with anything for anyone to present, so I thought that I'll actually give a very brief historical view of EPR and how actually, especially Einstein was corresponding with Schrödinger about this. So that's maybe first 10 minutes, and then I get to the actual thing, which is the quantum information formulation of this problem, so I'll build towards that, and then finally show this equivalence between incompatibility of measurements and the steering phenomenon. Two very different sounding things, but actually they are exactly the same. And then I have some summary. So EPR, like I said, EPR paradox, so this is about quantum mechanical wave function not being a complete description in some sense. So what do these guys mean with that? So this is now the historical part. This is really from the 35 paper. So somehow Einstein, Podolsky, and Rosen set, in a way, what they say a minimal, so this necessary condition for any definition of reality. So they talk about reality in this paper a lot. And what they mean by that, so they don't want to really define what is reality, but they say that there should be something called an element of reality in any definition of reality. And what they mean by this element of reality. So it's something, some sort of mechanism. So if I have a situation where some measurement gives a certain value with certainty, okay, so it is there, and I can check it without disturbing the system. So in a way I would say, okay, maybe I measure spin in direction Z in an eigenstate of Z, I will always get the same outcome. So then I would say, there is sort of element of reality behind that is responsible for this thing happening with certainty. This was their definition, okay? Actually, I have to say Einstein himself was not very happy with this, as we will see soon, but this was more from Podolsky and Rosen, this idea of element of reality. But using this definition, they can get to this kind of idea that the wave function is incomplete. How? Like I said, EPR paradox involves two parties. We can have A and B, Alice and Bob, who are, in principle, they can be far away from each other, space-like separated. And we take a quantum state, and here I should say, if you look at the original EPR paper, I do here a bit differently. They use position and momentum observables on an infinite dimensional Hilbert space, but you can make the point already with using two qubits. So this state you might have seen in your lectures, is the maximally entangled two-qubit state. If you haven't, it doesn't matter. Why I use the state, it's just, the point is that it has the following property, that if on system, so it's system A and B, if on system A, I measure some observable, like sigma Z, for example, get an outcome, say plus, I will know with certainty that if in the other system I were to measure sigma Z, I would also get outcome sigma Z plus. So this is just a property of this state. You can do the math, you can check it, but just you can trust me on this one, that this is what you will get. So in other words, what this means in other words is that, you see, I put the word certainty, with certainty there. So this is related to element of reality, because I'm measuring a faraway system, something, okay, on A, and I get an outcome, and I know with certainty in a space-like separated system that something will happen there as well, but as these are far away, because of locality, that has to be, I'm not disturbing the system B. So this actually, there has to be an element of reality behind this Z on system B. Because I can measure it, I can figure out what is the value without in any way disturbing the system. With certainty, because of the state is such. Well, the same thing is true if I look at sigma x or any other direction. So spin, if you think this is 2 electrons and this is just the spin measurement, or 2 photons as the polarization measurement, it doesn't matter which direction you measure, x or z, in a faraway system, you will know with certainty that the other system is also an x or z corresponding eigenstate. But this is a bit of a problem, because now I have simultaneous elements of reality for x and z both, because of locality. Like I said, whatever I do on A cannot instantaneously affect B because of locality. So I have actually simultaneous elements of reality in B. Why is this a problem? Well, because we know Heisenberg's uncertainty. Position momentum, or here sigma x and z, quantum state doesn't carry simultaneous information about them. So we know from basic quantum mechanics that the wave function doesn't contain this simultaneous information, but somehow it seems here, oh, but I can learn the simultaneous information about x and z, and hence this led EPR to conclude that quantum state, the wave function, has to be an incomplete description, because they thought that, okay, I can figure out x or z, whichever I want, but the state, quantum state can't do that, so then it has to be another theory than quantum theory that would explain this. Well, okay, so it seems like a paradox. We will hopefully resolve it. Yes, please.
But wouldn't this incompleteness just come from point 4 directly?
Exactly. But what we need is locality in order to say that they are simultaneous elements of reality. So we have to be space-like separated. Yeah, exactly. So that me, if I'm Alice, me measuring x or z, if you are far away, Bob, you don't get the information which one was it. Yeah, so, yes. Good question. Yeah, please ask any questions if you have. I'm very happy to clarify if I'm being unclear. Okay, so this seems like a paradox. So let's try to go a little bit further in history, like how this actually developed from here. So like I said, Einstein was not very happy with these elements of reality. So there was a little bit, straight after the paper, there are some letters exchanged between Einstein and Schrödinger. And Einstein said that, no, maybe we shouldn't talk about any elements of reality. It seems like a bit vaguely defined concept. So he said that instead how he would like to have to formulate this in the paper is that there are 2 possibilities in the measurement process, okay? So first of all, either measurements have definite values before they are performed. Yeah? If this is the case, before I perform a measurement, the values exist, then the wave function cannot be complete. Because wave function doesn't have them. It doesn't have them in it. It cannot contain simultaneous this information. So this is option number 1. So you see, Einstein is all the time reasoning towards incompleteness of quantum mechanics. He said option number 2 is that the values are created during the measurement. So they didn't exist before, but they are created the moment I measure. Well, this also leads to a problem with completeness, because if this is the case, and if wave function now were a complete description, then different wave functions have to describe different physical scenarios, right? If I have some object wave function that I say this is the complete description, that's all the information there is to know. If I have 2 different ones, well, clearly it's a different physical situation. I'm describing a different physical reality with that. So why is this a problem? Once again, because of locality. So if 2 different wave functions describe a different physical situation, locality says still that, okay, if I measure something on one system, it cannot affect the other system. It's the same argument as in the EPR paper, but without referring to any kind of element of reality. Yeah. It just talks about the wave function changing. And this actually starts to go towards the formulation how we understand steering today. We don't talk about any elements of reality. We talk about one party far away making measurements and that affecting the wave function of another party. And actually this went so far, Einstein actually was quoted saying that I couldn't care less whether or not, so the post-measurement state on this B system, if they are eigenstates of some observable. What does this mean? He doesn't care if it's an element of reality or not, because eigenstate would be an element of reality. So you see, Einstein wasn't happy with the EPR paper. He wanted to write it in a different way, talking about actually the state changing and not these elements of reality. And this he wrote to Schrödinger, and actually what I used here is from a later paper from Einstein, like 48 or so, he wrote the paper where he put it this way, but the essence is already in the letters to Schrödinger. Schrödinger replied to this directly, and this starts to go more towards what we do now in quantum information. Schrödinger replied to this, and I think this was where the word steering came from Schrödinger's replies. I think this was maybe the first occurrence of the word. So, but Schrödinger said that this dependence, so one party making some measurement, maybe the sigma z, getting an outcome. So this, whatever they do, this dependence of conditional state on system B is some form of steering from a distance. So steering, somehow altering the state from a distance. So clearly, Einstein and Schrödinger were both talking about just not about elements of reality, but just something happening far away, and that affects only the quantum wave function. Nothing to do with any eigenstates anymore. And actually, funny enough, this is pretty much the last point of this historical review, is that Schrödinger, there is a bit in this letter where he recalls a discussion already, you see, in 1920s. EPR paper was 1935. So clearly this effect was already on the table for a while before the paper came out. He said that, I'll read a small quote from him, this was a conference in Berlin, apparently, so he said that, that all the others told me that there is no incredible magic. You see, he uses the word magic, likes that word for some reason here. There's no incredible magic in the sense that the system in America gives x, I mean position, equal to 6. If I perform in the European system nothing on a certain action, well, it gives x equal to 5 if I perform another action. So you see, he really put like emphasis on the space-like separation. One is in America, one is in Europe, and he thought, well, there's some sort of magic. Like if I do something or nothing on one system, something is instantaneously changed somewhere else. So this looks, once again, like going against locality. And he continued that I can, by maltreating the European system, steer, once again, so he does the steering, steer the American system deliberately into a state where either position is sharp or where momentum is sharp. And he calls this magic. He didn't really find a problem. I think Schrödinger didn't find a problem with this phenomenon. But I think he also understood in the process there's no information conveyed. It's just the wave function. It's just the rule how we calculate probabilities that changes sort of instantaneously. But there's no information conveyed. So it doesn't really contradict locality in that sense. And actually Schrödinger went forward from here, showing two papers in the 30s showing that if I have a properly chosen quantum state between the space-like separated parties and I choose proper measurements, I can steer from a distance the other party to any quantum state I want. He showed this already in the 30s, which is quite a funny thing actually, because in quantum information, for those who are taking the course or have taken the course, maybe you have heard about this Jizan-Wouters-Jones-Hauer-Mensa theorem. It's actually this one already in the 30s. So people independently figure it out much later, at least in 2-3 groups. It was already in the 30s in this paper actually. And here the important point. So what is the point of this historical thing is that, okay, it started from elements of reality. If you read the original EPR paper, it doesn't seem like what we do today in quantum info, but actually just a few years after that, it was clearly understood it's not about any elements of reality, it's about wave function changing. And importantly, this we will see, now I changed the quantum info part, we will see there is no information conveyed in this procedure. Yeah. So the wave function can change, but for us to see the change, somebody has to tell what they did. So otherwise we don't see it. We will see this in the, it's encoded in this quantum info formulation. So this is sort of a small historical brief review, like how this developed. And these papers were in 30s, Einstein latest in 40s, and this theory was only formulated in 2007, I think, in the quantum info language. So there was quite a gap before people went back to it. If you have any questions about the historical part, I'm happy to answer now or after the talk. So now I'll just shift to the modern formulation. So a bit more math then. Yeah. Okay, good. Yeah, 2007. So how do we formulate this phenomenon? So it was something about two parties far away, want to make something, state changes on the other one. How do we encapsulate this all? The protocol is like this. In quantum info, we like to have Alice and Bob and all kinds of pictures. So here is the protocol for steering in quantum information. We have Alice and Bob. They share quantum state, rho AV. This is just a density matrix, or if you want, a bipartite of your vector state. How the protocol goes, and here comes the conveying of information in for the first time. How the protocol goes is that Alice has two measurements to choose from. So X here, throughout the talk, X is just labeled the choice of measurement. Here I just have one or two, so two different measurement boxes. So Bob asks Alice that, okay, we are sharing this state, so could you perform, say, measurement 1? So this one. Alice says, okay, good. So there's already classical information is exchanged at this point. And then Alice says, okay, good, so I got outcome, there are two outcomes, plus and minus. I got outcome plus, and Bob knows that he's in, like, he can keep a lab notebook saying that, this round, it was measurement 1 and outcome plus. Then they prepare the same state again. Okay, start over. This time Bob says, maybe measurement number 2. Alice, okay, fine, and outcome is maybe minus. And now Bob gives again lab notebook round number 2 was measurement 2, outcome minus, and so on and so forth. They repeat this many times, and in the end, many enough times that Bob can learn these states, so he can do tomography, or we call it tomography on his side. He can learn these 4 different sort of post-measurement states. He has labels for these, he can collect information, he can construct these states on pen and paper in the end. So these are 4 different states, and you see here's the point. There's classical information conveyed between, so X going here, outcome coming here, yeah? And only then Bob can see a difference in his statistics, otherwise he sees an average of these 4. Yeah. So in order for Bob to see the effect that he has different states, he has to know what that is. But which was measurement, what was outcome. So here's the classical info. So, okay, clearly there's somehow like we are now talking about post-measurement state, something is measured at the distance. And okay, here's the point I just explained, that Bob tells here's the classical info to Alice, input. So in this talk, always X means which measurement, and Alice tells outcomes, so outcomes I label A, so here plus or minus. How do we formulate this? If you've been to quantum info, great, you might know already. If not, no problem. I will tell you how to. So I want to see what these states exactly are. So first of all, what Alice does, how we model it in quantum theory is she performs a measurement. So I use here generalized measurements. If you haven't heard what that is, it's no problem. You can think of these as eigenprojectors of Hermitian observable. But in quantum info, we use also what is called positive operator value measure or generalized measurement. It's very simple. It's just like a generalization of probability distribution to operators. You see, so I have a collection of operators. X tells which measurement, A tells the outcome. These are positive semi-definite complex matrices with sum to identity. So like probability distribution is positive but sums to 1. So these are positive matrices summing to identity. And the probabilities of the experiment are just given by the Born rule. So that's the trace formula. Probability of getting outcome A when I measure X and have state rho is just a trace, like this. But like I said, you can think of these if you want, just as eigenprojectors of Hermitian observable. The only thing is I didn't put here that they have to be projectors, so there's slightly more general measurements, but these don't really change too much in this talk if you want to think in those terms. Okay, so Alice makes such a measurement, and now what I was interested in was this, how Bob's state changes. So this changes as follows. So if you have seen basic quantum information projection postulate, wonderful. Yeah, you know how state changes when I perform a measurement. Or if you've been to quantum info, you know that there is a Lüder's rule, which is basically the same thing, but just for generalized measurements. So how the state updates, you see as rho AB, the state they share. Alice performs an action, Bob does nothing. So it's Alice, something, tensor, so separate system, Bob, identity, nothing. So this is the updated state of the whole system. We sort of project on the eigenstate of measurement X, eigenstate A. And then, because I'm only interested in Bob, I trace out Alice. So this is the effect. Given some quantum state rho AB, Alice performs measurement. This is the effect I see on Bob's side, given that this X and A have been exchanged by them. Otherwise, I just see the average. So where's the steering? No way yet. It's just this is just building the formulation. So the definition is from this paper of Weissman from 2007. How he formulated what is steering, he said that okay, there has to be some quantum effect, and then we can call it steering. If I could classically explain these changes on Bob's side, I wouldn't call it sort of like something magic, like Schrödinger would say. So they define it like this. They say that there's no steering if I can explain these changes in Bob's state locally. So you see what I took here is a local ensemble of states. So P is always a probability here, P lambda, rho lambda. So that's an ensemble of states, yeah, collection of states. And I update this ensemble of states based on the classical information exchanged with Alice and Bob. So outcome of the measurement and which measurement was performed. If I can, you see, this is all local. This is just on Bob. Based on the classical information, I do some update. If I can explain the changes in Bob's side like this, I say there's no steering, there's no effect. Okay, something changed, but I can do it locally, so there was clearly no entanglement involved or something like this. Yeah. And this is just taken as the definition. And we can, if somebody wants to discuss why this is a good definition, we can discuss after the talk. Now we just take it as a definition. Okay, these models, if you look at the literature, it's not the most important point here, but these are called local hidden state models. So if you have been to quantum courses or heard about hidden variables, it's a bit similar, but it's hidden states. Yeah. So that's the definition of steering, how we see it today in quantum information. Any questions about this definition? Good. So I want to say a little bit, so now we can start asking questions. If we just take the definition like this, that okay, this is no steering. If such model doesn't exist, then I have steering. Now I can ask questions that, okay, is it a good definition in the sense that what do I need in order to have this effect of steering, to have this EPR effect? There are two things I can vary in my protocol. The shared state and the measurements Alice performs. That's all there is to it. That's all that characterizes this effect fully. So first, we can ask what kind of state we need in order to get this effect. Better not to be a classical state, classically correlated state, because then clearly we are not characterizing any quantum effect. And it turns out it's not. So, excuse me. So if I use a separable state, so this is state that is not entangled. The definition, you might have seen, if you haven't, no problem. The definition of a separable state is here on the top line. It's just, there's some p lambda again, so there's some convex combination, shared randomness. And we have locally preparable states. You see, we have some state on Alice, some state on Bob. There's no correlation between them in such a state. No quantum correlation. Now, if I look at the post-measurement states, line 2, post-measurement states on Bob's side, given I am using a separable state. I can just plug in this definition of the separable state. Partial trace is linear, so I get from line 1 to line 2. Yeah? Sum comes out, and partial trace just becomes this trace times rho lambda. But now the point is that what is this guy here? Well, this is just a probability. This is just a rule how to update my ensemble. I mean, this is just a probability distribution over A for each x and lambda. That was the property of this. This is the Born rule. So it's just a probability. So you see, if I use a separable state, what's the point here? Is that the changes on Bob's side can be explained with local ensemble p lambda rho lambda and some update on that based on the classical information shared between them. So there's no steering effect, which is wonderful in the sense that the definition is good, at least up to now, because I say that I need entanglement to get the steering effect. So at least I need some truly quantum effect in order to enable steering. But as it turns out, actually, entanglement is not always enough. It's only necessary. It's not always sufficient. I put a small picture here of states. So how these all quantum correlations are related in this bipartite scenario, I have separable, everything in this diagram is a state. Every point is a quantum state between two parties. I have the separable ones here inside. Then I have some which are entangled, this LHS, local hidden state, meaning unsteerable, not steerable. So there are entangled states which don't allow for steering. But also there's LHB, but these are the Bell local states. These are ones that have a hidden variable model, or in other words, don't violate Bell inequalities. Yeah. So there are states which allow for steering but don't allow for Bell violations, and then I have the ones which show that there's no local hidden variable model. So you see, this is sort of an in-between kind of correlation in quantum information between being entangled or violating a Bell inequality. There's another interesting class of states that includes some quantum effect in them, namely the EPR effect. If you want an example of such a state, you can take a maximally entangled state, add white noise to it, or so-called Werner state, and add noise to it. So it's a pure state. It starts, if you start to add noise to it, first it's on the border here, it violates Bell inequalities, then it starts to get inside slowly. It becomes such that it, for example, doesn't, it is entangled, they're entangled, but doesn't allow for steering, or allows for steering, doesn't allow for longevity. But okay, these are just the more specifics. If you come to quantum information course, you will see more details about these. But just to say that important point here is that entanglement is needed, it's not sufficient, and also there is this other class of Bell locality that is still a superset. So. Okay, so entanglement doesn't characterize this effect, but it's needed, so fine, it's clearly some sort of quantum effect. Now we can ask the same question about measurements. I said there are two things I can vary: shared state, Alice's measurements. Shared state has to be entangled. What about measurements? Well, actually, I make a small comment here about a historical comment on the first line. When the EPR paper came out, Bohr put on the same year a paper out explaining complementarity. So complementarity pairs like position momentum, sigma x, sigma z. These are pairs of observables. If I know the other one, it excludes all the information of the other. If I know the position exactly, it excludes the information about momentum. And Bohr actually said that, but the EPR conclusion is flawed because they are using complementary observables. So by definition, knowing one, you don't know the other. Okay, Einstein was maybe not too happy with this criticism, but that's another story. That was also partly behind his comment that I couldn't care less if it's an eigenstate. So it was a little bit a response to Bohr. Okay, so Bohr said that complementarity, why I put this here is that he realized that incompatibility of measurements plays a role here. So complementarity plays a role in the EPR effect. But as it turns out, complementarity is way too restrictive to characterize this effect because complementarity only applies to very specific pairs like position momentum. If I have position momentum, I add a little bit of noise, which will always be in an experiment anyway. They are not complementary anymore. But I can still have the EPR effect. Same for sigma x and z. I never make a perfect measurement. They're always a bit noisy. They're not complementary if they're noisy, but still they allow for EPR. So we need another notion to characterize the measurements that allow for EPR effect. And the other notion is in quantum information these days, what we use a central sort of classical to quantum border in quantum measurements is joint measurability. So what does this mean? I put a picture here before I give any mathematical definition. So this picture should actually be read from right to left. So you see, here I have two measurements. Measurement 1 and measurement 2. And now I put the outcomes, there's A1 and A subindex 2, just to make sure that on which one we are. So the question is that I have two measurements, and I ask, would there be a third measurement? So this would be also a measurement, this M, but this M is such, you see, it has two outcomes, a pair of outcomes, A1, A2. So the idea why it has this is that if I measure this M, and I get the pair A1, A2, I interpret A1 as being the outcome of the first measurement, and A2 being the outcome of the second measurement. So this is nothing but the generalization of joint probabilities to operators. If I have two classical probability distributions, they always have a joint distribution. But if I have two quantum generalized probability distributions, so when I talk about matrices, they don't always have a joint one. So I give the definition, I give a few examples what kind of measurements allow for a joint readout. Okay. That's the definition. I take a pair of measurements. These are generalized measurements, so you can just think about it. There's a collection of positive operators. They sum to identities like generalized probability distributions. We say that they're jointly measurable or compatible if there exists a single measurement, and usually the single measurement is now in the way that every outcome is a pair of outcomes. Every outcome associates to both measurements, A1 and A2, some outcome. And what is the relation between M and these A's? It's simply the fact that if I take a marginal of M, like I said, it's like a joint distribution. If I take a marginal, so you see if I sum over A2 of this, I get the first measurement. If I sum over the first marginal, A1, I get the second measurement. So this is just like reading a marginal of a probability distribution. But this concept turns out to be better to characterize quantum effects than complementarity. Okay, this also came way later. This didn't come when Bohr was alive, so. But Bohr realized that there's something to do with incompatibility, and this actually turns out to be the exact thing. This is very central in quantum theory these days, this concept. I would say it's as central as entanglement is in quantum states, is the fact that we have incompatible measurements in this sense in quantum theory. Okay, so example, what does this mean? I mean, if you use the first time, maybe it's a bit of a monster, but it's a rather simple concept. So what does it mean? I will just give the definition here, okay? So just to remind, that's just the definition from last page. First example, I can take a commuting pair. I mean, if I have commuting measurements, that's as classical as it gets. You know already from Heisenberg's uncertainty, the lower bound on this variance is 0. So let me take commuting measurements. Commuting pair, commutativity for generalized measurements means this. The for all outcomes of this commutator is 0. Okay, if you think about eigenprojectors, if eigenprojectors commute, the corresponding Hermitian observables commute. So this is really about commutativity of observables if you think it on that level, this condition. Okay, but this is not joint measurability. I just take two measurements which commute like this, and then the task is to find the joint measurement. This is the task. I'm given two measurements, ask, can you find the joint or not? And it turns out in this case I can. So what are the conditions? Okay, first of all, I'm a guess. That's a good guess, I can tell you. So, because why is this a good guess? If I sum over A1, remember, this guy sums to identity, I get A2. If I sum over A2, the second guy sums to identity, I get A1. So clearly it has the right marginals. And then you could say, yeah, but everything is jointly measurable because I will just use that, but no, that is not true. Why it's not true is that this kind of operator, you remember, these have to be positive matrices. This does not hold in general. If I take a product of positive matrix and positive matrix, actually rarely I get something that is positive. And it's also the case here. Only when they commute, I can write it as, okay, so that was the marginals. I already mentioned, sorry, I jumped ahead. So that's correct marginals, but the positivity is the important part. Why is this positive? It's because I can write it in this way. I can write it in the way where I have, you see, because of commutativity, A1 first of all is the same thing as square root of A1 times square root of A1. If A1 and A2 commute, the square root commutes as well. So what I have now here is positive operator A2 sandwiched with something. If I sandwich a positive operator with something, it remains positive. So this is indeed, this M is a quantum measurement. That's the limit. I can always find some distribution that has the correct marginals, but it might give me negative probabilities if I trace that against a state, and then I don't have compatible measurements. So it's the positivity is really crucial. So in order to have joint measurements. So what this tells is that, okay, fine, I'm giving you some new definition of compatibility of measurements, but actually, if I have commuting, so commutativity implies this. So this is somehow, okay, at least it gives the intuition that if I have something commuting, I can assign values simultaneously. Gives this idea from like Heisenberg uncertainty, if you wish. But that's not the end of the story. There are also non-commuting measurements. So let me keep the definition. I give an example of non-commuting measurements, which nevertheless allow you to measure them jointly, which sounds a bit paradoxical first if you have seen like Heisenberg. But this is true. So let me show you that. So I give the definition there, and a pair of non-commuting measurements. So what is a suitable pair here is to take, what are these? A lot of symbols, but it's very simple. The first measurement, these are eigenprojectors written in the Bloch form of measurement sigma z, except I put some mu there. That's a noise parameter. That's the length of the Bloch vector. So if it's a projector, it's 1. If it's less, there's noise in it. Yeah. Same for this A2, it's a sigma x. Same thing, it's eigenprojector of sigma x, but I added a little bit of noise. So this mu parameter is between 0 and 1. So I didn't include 0 because if I include 0, then this commute for that choice. But for other choices, they don't commute. So how do I measure these jointly? I have x and z like this. So the idea how to measure jointly is to measure in 45 degrees tilted directions. See if it's plus and plus, z and x. Well, I measure in these directions. If I get this outcome, it's plus and plus. I get this plus and minus, and so on. So I just guess a joint measurement once again, and this is now a joint measurement which for non-commuting measurement. So you see, this is just a technical way of what I just explained. I measure in a direction between x and z. That's just what it is. A1 and A2 are plus minus 1, and I put the noise parameter mu there. Now, the important thing is this positive? That's the first. It has the correct marginals. This you can check yourself if you want. But is it positive? It is positive, but it depends on the mu. So positivity is if and only if this mu is less than 1 over the square root of 2. Why is this? Okay, look, I put the small color there in case you want to check the slides later. I put some additional information. Why is it? Well, positive semi-definiteness of this kind of Bloch form operator is equivalent to the Bloch vector having length which is less than 1. But okay, that's where the 1 over square root of 2 comes. Because here, you see, I have a vector, Bloch vector, whose length is, so 1 in the direction, z1 in the direction of x, it's square root of 2, the length, times mu, has to be less than 1, and 1 over square root of 2 is the limit. But this is, okay, and like as the marginals, you can check yourself if you want, or you can believe me that it gives the correct marginals. It's a very direct calculation, I'm going to go through here. I'm just going to tell the point. These are non-commuting measurements, and they allow me to assign a value simultaneously to both of them. Sounds very counterintuitive if you have heard explanations about Heisenberg's uncertainty. If you go to basic quantum mechanics course, the intuitive explanation we are given is something like, because the variances, the sum or the product has a lower bound which is not 0, hence I cannot simultaneously assign values, or they disturb each other. But that's not at all what it says. It says that quantum state cannot contain information. It says nothing about, you see, this is the hand wavy explanation there. This is the exact way of saying, can I put simultaneous values to measurements? Heisenberg's uncertainty doesn't really tell you that, it just tells something about variances. But the intuition is, of course, behind this. Okay, so that's joint measurability. I know a lot of new concepts, but that's the last new concept that's gonna come, because now I'm just gonna show how this relates to quantum steering and how this is actually exactly the same thing, which sounds a bit weird because steering was two parties far away. something about the state, and now I just say, no, but it's actually this phenomenon. So it's one single party. So let's check why it's the case. Any questions about joint measurements? Happy to also take questions afterwards. Okay, bringing the two together. So like I said, in steering we had these Alice and Bob far away. What was important for steering is this post-measurement states on Bob's side, and the model we are asking for was this some local ensemble updated based on classical information shared between the parties. That's one side of the coin. The other one is incompatibility of measurements. They look very different physically, the problems. What's the question here? I have two measurements I ask. Can I simultaneously assign values to them according to this formula? So what's the connection? Well, I use the notation so that if you would just see the slide the first time, maybe you would see that there is an A here, a measurement, and the measurements A here. So indeed, it's about what kind of measurements Alice uses in this task characterizes it. So first of all, I'm going to show, so there are two steps. I will just show that if I use compatible measurements, I will not get the steering effect. And then I will show the more surprising part, which is the other side. So the first part is rather simple. So let's put compatible measurements for Alice here and show that we get this non-steerable model. Yeah. So I will just take now look at the post-measurement state for the first measurement, and the second goes similarly. I'll just go in detail the first one. So that's the post-measurement state, that's the definition. And now what I do, I just insert the definition of joint measurability. I know what is A1. It's just the marginal of some m, because I assume they're jointly measurable. Sum comes out because partial trace is linear. This is actually already an unsteerable model. It doesn't look like it, but it is. I can write it in the following form. You see, I will soon tell what this rho and p are, but the point is that you see the local states on Bob, these will be local states on Bob. I have some ensemble of them, and I am updating it. I'm classically processing it. Taking a marginal is classical processing. So this is actually a non-steerable model. So what are these operators here if you want? I mean, I'm just rewriting this term in this form. So if you want, the probability is just outcome probability is there, and the post-measurement state is just this one. So this is, if you want to look at the slides later, just the additional info. The point is, if I have something jointly measurable, there's no steering. So yeah, two-line calculation, 3 lines. So great. Similar goes for A2, so it's yeah, you will get the model from there. Okay, and okay, if you really want to be pedantic, I put here just more for the fact that if you want to check the slides later, what is your lambda that was before it's just the pair of the outcomes. Okay, so joint measurability does not allow for steering. Neither did separable states. But now the surprising part is that as entanglement is not enough for steering, incompatibility actually is. This is where the two concepts really combine. So joint measurability doesn't allow for steering. Let's go the other way around. Bring the two together. So now I need a small trick, which I can prove after the lecture if you want, if you've never seen it, but it's just to go smoothly here. So, okay, let's now take for Alice an incompatible pair, a pair that is not jointly measurable, and use a very special state. This is the maximally entangled state, yeah, vector state. This state has a very special property. It was already earlier. It's like the psi plus I had earlier where I had sigma z and x perfectly correlated. So this has the very special property that with this state, Bob's post-measurement states read as follows. First equality is just the definition of post-measurement state, but this state has a very special property that whatever Alice does, it comes straight through on Bob's side. Okay, there is the 1 over d, Bob's there, and transpose. Why is this the case? There's a small trick I leave there. If you haven't seen it, I can show the proof. I can show how to with that trick get this equality here. For now, you can just believe me that this psi plus is very special in the sense that whatever Alice does goes straight through to Bob. Bob sees it directly. There's just this transposition 1 over d in front, but these are post-measurement states. So now I make a counter assumption. This is a technical part here. So I make a counter assumption that I wouldn't get steering. So I have incompatible measurements. I have chosen a very nice state that really brings everything from Alice to Bob. I make a counter assumption that this is unsteerable, and I show it leads to a contradiction. If it does, it's actually steerable. Okay. So counter assumption. This is unsteerable. So this is the definition of being unsteerable. What does it mean in this case that we know rho Ax is that guy there? Well, let me just multiply the d to other side, take the transposes. Yeah. Only thing that gets transposed is the rho lambda because that's the only operator, everything else is numbers. So now there's the trick. I want to show a contradiction. I show that these AAX are actually compatible. So I define a joint measurement. This is not a joint measurement yet, but I define a measurement. This is a trick that was about 10 years ago we did this paper. So the trick is that I define a measurement. You see, I take everything here, so the d lambda and rho lambda, everything that has only lambda, I put them together. This surprisingly is a measurement. Okay, it needs to be positive and sum to 1 in order to be a measurement. It is positive, it's two positive numbers, d and b lambda, and it's a positive operator. Transposes doesn't change positivity. It is positive operator. Why is the measurement? Why does it sum to identity? Small calculation. If I sum over lambda, okay, that's a definition of g lambda, but here's a small trick. I will just multiply by 1. You see the multiplication by 1. I put sum over a PAX lambda. That's the probability distribution. I multiply by 1, and tada! What do I have here? D, P lambda, rho lambda transpose. It's just this exact guy here. So it's AAX, which is a measurement, hence I get identity. So a small trick to show that this is actually a measurement, and this actually is a joint measurement. So you see, I start from the fact that I have no assumption something is non-jointly measurable. If it were unsteerable, I come to a contradiction. Hence, it is actually steerable. Maybe it's not obvious from here yet why this is a joint measurement, because a joint measurement gives you simultaneously the values. I will show why this is actually a joint measurement. So you see, we got for AAX, we got this model, some measurement, and some sort of classical processing. That's already very close. The only trick to go from here to this kind of joint probability distribution with correct marginals is this is the trick. It's very simple. So I need to define my M, which is the actual joint measurement. I just multiply the two post-processings or classical processings together and put G lambda. Why does this have correct marginals? Okay, first of all, it's positive clearly, because everything inside is positive. Why does this have correct marginals? Let's sum over A2. A2 is only in this term. It's a probability. It gives me 1. So I'm left with sum over lambda, this probability G lambda, which is exactly this. I get AAX. Correct marginals. So I actually get something jointly measurable. So I started from incompatible, and if it were unsteerable, it wouldn't be incompatible. So it's a contradiction, so actually it is steerable. This shows that, first I showed that if I have something jointly measurable analysis side, I don't see steering. Now I showed if I have something incompatible, even the slightest bit incompatible, I can steer, given that I choose the correct state. And that's the result. That's the connection. The original connection between incompatibility and steering is that Alice far away can steer Bob if and only if she uses incompatible measurements in the sense of being non-jointly measurable. Well, I promise that there's a full mathematical connection. This is already sort of it. It says that, okay, EPR effect is characterized exactly by incompatibility, especially because EPR used exactly this type of state in their paper. It was infinite dimensional, but they used the equivalent of this. And the same proof with slight technical modifications goes through in infinite dimensions, but I'm not gonna do it here. So yeah, in a way, Bohr was already right in the sense that complementarity prevents the paradox, so there's no paradox. It was a joint measurability that characterizes this effect, so that was in the heart of it. But actually one can take this one step further. I give one more, even stronger link, and then I give the summary, and that's all. So I can do even stronger link than this. I don't even have to talk about analysis measurements. I can do a mathematical link. So an even stronger link. I take the definitions here, unsteerability and joint measurability. Now you see I put my P lambda here, just to make the two definitions even closer. On the last slide, we saw joint measurability. We don't need marginals. It's enough to have some classical processing. Yeah? So they look really exactly the same. Only difference is that these problems are normalized differently. On the lower line, these sum to, if I sum over A, these objects sum to identity. Same for G. If I sum over lambda on G, it gives identity. On the top line, if I sum over A here, what I will get is just a quantum state. This will actually be, if I rho AP originally, this will just be Bob's share of that state. Okay, so this normalizes to a state, and same thing P lambda, rho lambda, it normalizes to a quantum state, not to identity. But look, the problems look exactly the same, and the trick is just to find how to renormalize so that they are mathematically exactly the same thing. The trick is this. I take this sum, I take the normalization of this rho AX, I just say it's some rho as a definition, and I define some measurements with this formula. You see, I use the inverse square root, so if my state doesn't invert, I invert it in the subspace, it's invertible. So if it's a zero eigenvalues, I don't care about that subspace, I invert it where it inverts. These are measurements. Why? Well, everything is positive, and you see rho AX sums to rho, so hence A tilde sums to rho minus half, rho minus half. That's identity. So these are measurements. But no, these are not anything. These don't necessarily have anything to do with the actual experiment I'm doing. This is the mathematical trick at this point. Earlier it was Alice's physical measurements. Now it's just a mathematical trick to connect the two problems in a one-to-one manner. So now it's not too hard to see that if I have unsteerable states, then these measurements are jointly measurable. Because I have renormalized rho AX, which means that I renormalize this P lambda, rho lambda, and it turns out it gives me a P of Vn. This is a calculation you can do by yourself if you want. It's very straightforward to see. Other way around, if these, this mathematically defined P of these measurements are jointly measurable, then I renormalize. I go to normalizing them to be states instead of measurements. If they're jointly measurable, I just sandwich my G lambda with the rho half, and that will be my local interstate model. So in this sense, these problems actually are the exactly same thing. This is a very different normalization. And the result is like this. If I want to decide steerability of something and there's a typo, steerability is equivalent to non-joint measurability, not joint measurability. It's equivalent to incompatibility of these measurements. So there is even a deeper mathematical link between the two. Just the same. It's just about joint distributions in the end. Different ways of generalizing a joint probability distribution. That's all it is about, this steering effect in language of quantum info. So we came quite away from elements of reality, which seem maybe a bit vaguely defined concepts. What are these? What should they be? How should I model them mathematically? Through Einstein and Schrödinger, for modern formulation, even taking into account Bohr, to say that actually, yeah, it was joint measurability all along, the whole problem that they were talking about, although it looked very different because it was in two space-like separated systems. And to summarize, what was very important point I said in quantum steering, there's no information going faster than light. The wave function changes, but it was really Alice telling Bob what she did. Only then Bob can see the changes in the state. Okay, what the steering effect requires, it requires entanglement. So not any state will give this, but it really says that we had to ask the right questions. So we had to asking questions from quantum system means making measurements. We had to make the incompatible measurements. So and mathematically, these are fully equivalent concepts. So there's really no difference. If you solve the steering problem, you are solving the corresponding joint measurability problem, or vice versa. And yeah, to finalize, I will just put a few references here. So there's the EPR paper, the original I started from, the quantum info formulation. If you are interested in the historical aspects, we wrote a review a few years back where we went through, and then these letters of Einstein and Schrödinger are actually in more detail in that review explained, and also this, how already in 30s Schrödinger understood that it's about how the steering works, that I can steer one system into any state I want. And then, okay, if you want this joint measurement connection, these are works done in Geneva, this one, the first one, and then the two others are when I was in Germany as a PhD student. So with this, I would like to thank you all for the attention.
Thank you. Are there any questions? Okay, maybe I will start. So I have a question about the model when you described the noise when you divided by square root of 2.
Yeah.
And you said that it works for the basis when you rotate it for 2.5.
Yes.
But I guess if you don't rotate it, but still include the noise, it's just so
yes.
rotation is not needed in this case.
Yes, so let's see. So yeah, the point is why I took 45 degrees was that this will give the correct marginals. So if I sum here over A2, I get here plus and minus, so that term goes away. I get all the other terms that have A2, I get them twice, so I get exactly this guy. I could measure in some other directions, but the marginals would be different, or alternatively, I get the right marginals, but then I will not get the same noise for both X and Z. I would get maybe very sharp X, but very noisy Z. Yeah, so that's the...
Maybe another question about this formula, why mu cannot be 1?
It can be 1, here.
Yeah, exactly.
Yeah, exactly. So it's because these operators have to be positive semi-definite in order to represent measurements. And if mu was 1, then the length of the... So this is the Bloch representation of the measurement, or the elements of the measurement. If mu was 1, the length of this Bloch vector would be square root of 2, because A1 and A2 are plus or minus. Yeah, and then it would be a negative operator, and hence it's 1 over square root of 2, the limit. And this is actually optimal. I didn't say it in the talk, but if I go above 1 over square root of 2 plus epsilon, they are incompatible from that.
Okay, and the second question is about the very beginning. So when you described local heater models, is it the only way to describe them?
So this was it in the beginning of steering?
I guess it was in the introduction.
Let's see.
So when you speed up the sum of the lambda.
Yeah, yes. Okay, so it's here. This one, P lambda. What's this one? The local model. Sorry, it only appeared for me. This one.
It's exactly.
Well, it's not the only way. It's not the only way, but it's turned out that it's a very good thing to pick because it captures the notion of entanglement in it, the incompatibility. But I can actually write it, because maybe this concept is maybe a little bit weird. This is actually just classical data processing. But if I make an assumption that this lambda and x are independent variables, I can write it in a different way. So maybe I just, can I go above it so that it's still visible? Yeah. So I can rewrite it in a way that is maybe a little bit more capturing the idea that I'm updating something based on classical information. So what I can do is take that, and now I guess everyone knows Bayes' formula, yeah, for conditional probabilities. So this one is the probability of all of these guys divided by px lambda, given that px joint probability px lambda is not 0. Yeah, so this I have to assume now to go forward that that's not 0. And so now the trick here is if I assume more whether x and lambda are independent variables, just mean that the joint probability factorizes. Yeah, so that I can write the whole thing as I have p lambda, I have probability of all together, x lambda, and then I have px p lambda. Okay, that's just assuming that they are independent, the variables. Those go away. So I have px lambda and px. Now I need to do a small trick. Namely, I have to multiply this. So maybe I pull this down, it's easier for me to write. So I have to multiply this by, let's see. Yes. I multiply by 1. So I take this. Divide by P. I think that's still the same quantity. Yes, yeah. It's just by multiplying by 1. So you see what I get here is probability of AX, sorry, lambda given AX. Okay, with a few assumptions, the model actually reads, so putting all together, I'm asking, do I have a model? You see PA given X, just normalization, nothing there. And then I take this part. And what was was it rho lambda? So now you see I'm really having a local ensemble. And the priors are just updated based on the classical information AX. So that would be another way of formulating it. Under a few assumptions that probability of X and lambda is not 0, they're independent. But now I'm really asking, can the effects be reproduced? No need to care about that normalization. Can they be reproduced from a local ensemble? Where only priors, not even the quantum state, not even that gets updated. Only the classical information gets updated. So that would be another way of formulating it.
Maybe we can ask because I have a comment here. So are there any other questions?
I did not quite understand at which point in your argumentation you could conclude that the information spread through the entanglement is not faster than light.
Okay, yeah. Yes, okay. So the point is that when we look, actually, I can do it on this slide. So I didn't explain it in detail. So the point is here. So these, you see this rho x, how it's defined. So if A is not known to Bob, so if Alice doesn't tell what A is, what's the state Bob is having? He cannot know, he knows that, okay, it's some rho x, but the A is missing. So what's the state he has? There's no update for him, right? It's just some A that happens. I might know it or not, but if I don't know it, what is my state on Bob's side? It's simply just this one. Yeah, it's just that one. So because he has no information about A, this is identity. So when there's no information, this classical information is not conveyed to Bob, this all just looks like trace over A of the shared state. So he doesn't see the effect unless it's told to him that which one it is. So it's always it's independent of how the state updated because he doesn't know that it updated. Yeah. So only to see this effect, he has to have the label A. Yeah. Otherwise, for him, he doesn't see the difference. Yeah.
Other questions? Okay, I guess then we can continue on the apero. Let me check if there are any questions in the Zoom. If you want to ask the question, please write to the chat. Then we can mute you. I guess probably not. And let's thank Roope again.